Integration is generally more difficult than differentiation. There are no fail-safe methods for finding an antiderivative, and in some cases, there is no elementary formula for the antiderivative. However, there are several general techniques which can be applied in many situations. One of them is the substitution method. Since integration is the inverse process of taking derivatives, most of the differentiation rules have corresponding integration methods. Today we will learn the substitution method, which is the chain rule in reverse. As an example, consider function sine of x squared. According to the chain rule, the derivative of sine of x squared is 2x cosine of x squared. This says that sine of x squared is an antiderivative of function 2x cosine x squared. Therefore, the integral of 2x cosine of x squared equals sine of x squared plus c. Here, x squared is the inside function, and 2x is the derivative of the inside function x squared. The expression under the integral is the product of a composite function and the derivative of the inside function. We cannot reverse the chain rule if the derivative of the inside function is missing, which means we will not be able to compute the integral of just cosine x squared. In general, this method works when we can rewrite the integral as an integral of a product of a composite function f of u of x and the derivative of the inside function u prime of x. If capital F of u is an antiderivative of f of u, then by the chain rule, the derivative of f of u of x equals f prime of u of x times u prime of x. Since the derivative of capital F is lowercase f, this equals f of u of x times u prime of x. Therefore, the integral of f of u of x u prime of x equals capital F of u of x plus c. This formula represents the substitution method. The procedure to carry out substitution uses differentials. Recall that when u is a function of x, the differential of u, denoted by du, is u prime of x dx. If we make substitution u equals u of x, then f of u of x becomes simply f of u, and our integral can be written in terms of the new variable u as integral of f of u du. We arrived at the following rule. Integral of f of u of x, u prime of x dx equals integral of f of u du. The substitution rule is often referred to as the change of variables formula. It transforms an integral in the variable x into a hopefully simpler integral in the new variable u. Let's consider the following example. Integral of 1 plus 3x squared times square root of x plus x cubed dx. This integral contains the composite function square root of x plus x cubed. The inside function is x plus x cubed, and the derivative of the inside function is also appears in the integral. Let's rewrite the integral in a way which resembles the left-hand side of the substitution formula. Integral of the composite function square root of x plus x cubed times the derivative of the inside function 1 plus 3x squared dx. Now u is x plus x cubed and du is 1 plus 3x squared dx. After the change of variables, we obtain integral of square root of u du. Now we just need to find the antiderivative of square root of u. By the power rule, antiderivative of u to the 1/2 is u to the 3/2 times 2/3 plus c. The last step is to change the variables back to x. We replace u by x plus x cubed and obtain 2/3 x plus x cubed to the power 3/2 plus c as the final answer. We can check our answer by differentiating 2/3 x plus x cubed to the power 3/2. We get 2/3 times 3/2 x plus x cubed to the 1/2 times the derivative of the inside function 1 plus 3x squared, which is square root x plus x cubed times 1 plus 3x squared, exactly the expression under the integral. When using the substitution method, we implement the following strategy. First, choose the function u and compute du. The key step is to choose the appropriate function u. Since the substitution method is directly related to the chain rule, the inside function of a composite function is the most likely candidate. Next, rewrite the integral in terms of u and du and evaluate. Remember that you must put everything in terms of the new variable u. It is not permissible to have both x and u in the same integral. The last step is to express the final answer in terms of x. Now we go over several examples. The first one is to evaluate integral of 2x times x squared plus 5 to the fourth dx. This integral contains the composite function x squared plus 5 to the fourth. The inside function x squared plus 5 is usually a good candidate for u. We set u equals x squared plus 5. Then du equals 2x dx, which also occurs in the integral. We make the substitution and obtain the integral of u to the fourth du. By the power rule, the general antiderivative of u to the fourth is u to the fifth over 5 plus c. We rewrite this in terms of x by substituting back x squared plus 5 for u. The final answer is 1/5 x squared plus 5 to the fifth plus c. The next example is to evaluate integral of x divided by square root of 1 minus 4x squared dx. The composite function in this integral is square root of 1 minus 4x squared, and the inside function is 1 minus 4x squared. This suggests the substitution u equals 1 minus 4x squared. We compute du equals negative 8x dx. This expression does not appear in the integral. What does appear is x dx. To remedy the situation, we divide both sides of this equation by negative 8 and get negative 1/8 du equals x dx. Note that we can multiply or divide the expression with differentials by a constant because of the constant multiple rule for derivatives. we cannot multiply or divide by a variable. We carry out the substitution and obtain negative 1/8 integral of 1 over square root of u du. Now our task is to find an antiderivative of 1 over square root of u. We rewrite this integral as negative 1/8 integral of u to the negative 1/2 du and use the power rule to get the antiderivative negative 1/8 u to the 1/2 over 1/2 plus c. This simplifies to negative 1/4 square root of u plus c. Now we return to the original variable x by replacing u with 1 minus 4x squared. The final answer is negative 1/4 1 minus 4x squared to the 1/2 plus c. The third example is to evaluate the integral of x times square root of 2x plus 7 dx. We recognize that square root of 2x plus 7 is a composite function, so the inside function 2x plus 7 is the usual candidate for substitution. We set u equals 2x plus 7. Then du equals 2 dx. As before, we divide by 2 and obtain that 1/2 du equals dx. However, there is an extra factor of x in the integral. Remember, we must put everything in terms of the new variable u. To take care of an extra x, we solve equation u equals 2x plus 7 for x and get x equals 1/2 times u minus 7. Now we can carry out the substitution. We obtain integral of 1/2 u minus 7 times square root of u times 1/2 du. This simplifies to 1/4 integral of u minus 7 times u to the 1/2 du. We have seen such integrals before. Since there is no product rule for integrals, the trick is to multiply out, get a sum, and use the power rule for each term. U times u to the 1/2 gives u to the 3/2, and negative 7 times u to the 1/2 gives negative 7 u to the 1/2. After applying the power rule, we obtain 1/4 times u to the 1/2 over 1/2 minus 7 u to the negative 1/2 over negative 1/2 plus c. We simplify and get 1/2 u to the 1/2 plus 7/2 u to the negative 1/2 plus c. The last step is to replace u by 2x plus 7. The answer is 1/2 2x plus 7 to the 1/2 plus 7/2 2x plus 7 to the negative 1/2 plus c. There are two ways of using substitution to compute definite integrals. One way is to evaluate the indefinite integral first, and then use the fundamental theorem of calculus. For example, let's evaluate integral from 0 to 4 of 2x plus 1 to the 7th dx. To use the fundamental theorem of calculus, we need to find an antiderivative of 2x plus 1 to the 7th. Therefore, we evaluate the indefinite integral of 2x plus 1 to the 7th. This is the integral of the composite function 2x plus 1 to the 7th. So we set u to be the inside function 2x plus 1. Then du equals 2 dx. We divide by 2 and get 1/2 du equals dx. We make substitution and obtain 1/2 integral of u to the 7th du. By the power rule, it equals u to the 8th over 16 plus c. Now we return to our original variable x and obtain 1 over 16 2x plus 1 to the 8th plus c. By the fundamental theorem of calculus, the definite integral from 0 to 4 of 2x plus 1 to the 7th dx equals the difference of values of an antiderivative at the upper and lower limits. Taking x equals 4, we get 2 times 4 plus 1, which is 9, to the 8th power over 16 minus the value at x equals 0, 1/16. So the answer is 9 to the 8th over 16 minus 1/16. The other way to evaluate this integral, which is preferable, is to change the limits of integration when the variable is changed. The substitution rule for definite integrals states that the integral from a to b f of u of x u prime of x dx equals integral from u of a to u of b f of u du. This rule says that when using substitution in a definite integral, we must put everything in terms of the new variable u, including the limits of integration. The new limits of integration with respect to the u variable are u of a and u of b. Think about it this way. As x varies from a to b, the variable u of x varies from u of a to u of b. Let's evaluate the same integral from 0 to 4 to x plus 1 to the 7th dx using the substitution rule for definite integrals. The first step is the same as before. We choose u to be the inside function 2x plus 1 and compute 1/2 du to be dx. The lower limit of this integral is 0, so we plug in 0 for x into the formula for u. We get u of 0 equals 2 times 0 plus 1 equals 1. Similarly, the upper limit is 4. We plug in 4 for x into 2x plus 1 and obtain u of 4 equals 2 times 4 plus 1 equals 9. After substitution, we get 1/2 integral from 1 to 9 of u to the 7th du. We compute this definite integral to be u to the 8th over 16 from 1 to 9, which equals 9 to the 8th over 16 minus 1/16. The answer, as expected, is the same as before. Our last example is to evaluate integral from 0 to square root of pi over 2 x times cosine of x squared dx. The composite function in this integral is cosine of x squared. We set u to be the inside function, x squared. Then du equals 2x dx. Since constant 2 is not present in the integral, we divide this equation by 2 and get 1/2 du equals x dx. Now let's compute the new limits of integration. The lower limit, u at 0 equals 0 squared equals 0. The upper limit, u of square root of pi over 2 equals square root of pi over 2 squared equals pi over 4. The integral becomes 1/2 integral from 0 to pi over 4 cosine u du. Since an antiderivative of cosine u is sine u, we obtain 1/2 sine u from 0 to pi over 4. This equals 1/2 sine of pi over 4 minus sine 0 equals square root of 2 divided by 4. This is the end of our lecture.